I'm Eda. I work at Intel Labs as a research scientist, and I'm going to present our work called NLU for game-based learning in real and our initial evaluations. So this is like a joint work from my colleagues in Intelligent Systems Lab, and our team is called focusing on multimodal dialogue and interaction applications. Okay. Thank you. Sorry about that. So this is the very generic outline of my talk. So I'm going to introduce the problem, what is the application domain, and I'm going to try to give you some background information about the architecture. And I'll talk about our natural language understanding models, and I'll try to share some experimental results with what kind of game data sets that we collected and what are our intent recognition results. And I will end with some conclusion and future work. So this is I would say, brief summary of the talk. So we are aiming to build intelligent systems that are designed for play-based interactions, and these are multimodal AI systems, and they should be contextually aware of the users and their surroundings. So here, the contextual awareness, the part that we focus on is the understanding the language of the users first. And so we focus on the spoken dialogue systems of the overall intelligent system architecture, because we believe, it's the critical part for carrying out an effective goal-oriented communication with the real players. And this work basically focus on the real world or in the wild deployment issues. Because, if you really, you can build a system in the lab, but when you try to deploy it in the wild, there will be lots of issues, as you might imagine. And we need to make the whole spoken dialogue system more robust. So that's the end goal. And the module that we focus on is here the natural language understanding, and the main task that we focus on is intent recognition. And we actually explored potential benefits of different architectures and different embeddings for improving the intent recognition overall. And another issue other than the in-the-wild deployment is the small size tasks, so small size data sets. So these are very task specific, game specific, and domain specific data sets, and collecting them is very painful, as you know, and it's very expensive basically. So we need to get used to working on these small size data sets and try to make it more robust, no matter what the size is. And we collected some evaluation data sets from children at school. So we had a real school deployment in authentic classrooms. And they are basically practicing basic math concepts, and they are playing games while doing that. And that's why it's a game-based learning system, because the literature says, especially for that age group, we are focusing on 5 to 8 years old kids. The engagement is very critical, and games are the best ways to do that. So that's the motivation. And we evaluated the NLU performance on our initial proof of concept game data first. And then we compare it on the real world deployment data sets. So we want to see, how much performance we're going to lose. And compared to the more straightforward architectures, we investigated real intent and entity transformer. It's called DIET. So this is a fairly recent architecture proposed by the authors in RASA. And we found that it's robust enough for our use cases. Both for the POC data sets and still in the real world data, although there's some, the performance degradation. So this is the application domain. So we are trying to come up with some educational games, and the project called Kids Space. So we are building the smart spaces for kids, and the kids are basically learning basic math concepts via gameplay and play-based interactions, and these are multimodal interactions, as you can see. So they are trying to learn the concepts of tens and ones. So they are trying to construct some numbers. And here the larger pots, actually flower pots, represents the tens, and the smaller ones actually represent ones. So we're gonna ask like, can you plant 6 flowers? And the kids should ideally put the 6 small pots against the wall. And it's projected on the wall, and when they put the correct number of pots against the wall, the flowers will bloom. And in the second game, this was the planting game, the very general idea. And the second game was watering game. So here we had a number grid on the wall again. And our virtual agent, Oscar, the teddy bear here, he's asking a certain set of questions. Like it's like an achievement-based, gradual achievement-based game. So after they correctly answer 4 consecutive questions, the water will come up from the number grid and the flowers will grow. So that's the magic effect, and kids really love it. I mean, both the planting game and watering game. It's really, I think, we believe it's a very fun way to learn these very basic concepts. And since these are like the mostly first graders, it's not that straightforward to them, and we really have very positive engagement results. So this is the overall spoken dialogue system architecture. So what we focus on here is the NLU module, as I said, the natural language understanding, and specifically the intent recognition. But the multimodal aspect comes into play in the dialogue manager side. This is not in the scope of this work, but just to give you an overall idea, like we have these physical manipulators, like the objects in the scene, like the large pots and small pots, and also we need to detect the gestures and certain actions that the kids do, like touching the wall for picking the right number on the number grid and things like that. And also the audio context is important, because this is a multi-party conversational setup. So there are 2 kids in the room and 1 adult facilitator. He or she is helping the kids go through the game, because a lot of things can go wrong, as you might imagine. So we need to detect who's saying what, because the system is always in always listening mode. There's no keyword spotting or anything like, you know, hey Google, Alexa. So there's nothing like that. The system is not activated when they say Oscar. So Oscar is actually always listening. And the real challenge is, you know, understanding if the kids or the facilitator is really referring to the agent, or are they talking to each other. So that's one of the main challenges. So that's why, I mean, for all these reasons, the system should be multimodal. For the NLU models, we actually in the SDS pipeline, as I showed, the NLU modules is, or the whole pipeline is built on top of the Rasa open source framework. So this is maybe some of you have worked on it. I mean, it's a great platform. I mean, it's fully open source. It's a lot of like community support and everything. And it has like, for such kind of like bootstrapping the dialogue system, we find it very, you know, easy to use and suits our purposes. And you can, of course, like change anything you want in the system. So it's fully open source. And the former baseline intent classifier in the Rasa was actually like mostly an embedding-based classifier. So it's inspired by this star space algorithm. It's proposed by Facebook in 2018. It's an approximation of like, how can we really train like supervised embeddings instead of like the unsupervised ones that we all used to have, like just trained on unlabeled corpora. These ones are like, they're actually training together with the intent labels and the whole utterances together, and try to increase the similarity between those labels and the intent clusters. So, and also try to penalize try to penalize the negative samples at the same time. So it's just pairing and trying to learn the better embeddings by checking the similarity and doing some ranking. So that was the baseline algorithm. But what we did in 2019 is we just thought that it was, you know, the Rasa does not have the integrated transformer-based intent recognition yet. So we did that, and also we incorporated the pre-trained word embedding instead of this star space algorithm. And we saw great improvements by doing that. But then Rasa, of course, updated their models as well. So this is like, I mean, it's a very, you know, the large community, it will be like improved all the time. And you can like, we believe you can always like check for state-of-the-art stuff, eventually will be there. So the next thing that we tried in this work is using the diet and convert. So diet is, as I mentioned, is a multitask architecture. So you are learning both the intents and entities at the same time, doing some joint learning. And also we incorporated the conversational representations from transformer. So these are better than BERT embeddings, the convert, and it's more like efficient. I mean, it's a lightweight architecture. Both diet and convert are memory efficient, and also like, I mean, it's much faster to train, and it's more convenient for our use cases as well. And also for the ablation study, we also checked the diet plus BERT. So just to see the effects of switching from TF to diet and also switching from BERT to convert. So this is the dataset statistics. So on the left, we are showing the proof of concept dataset. So this means that we actually start from the UX script. So we have user experience team. They have interviews with the teacher, parents. So they kind of envision what kind of interactions the kids would have with such an agent, and what you know, what would they probably say to the agent, or I mean, what kind of utterances should we expect? So we started from there. We had some samples, and also we enlarged that set with some in the lab data collection. So this is very limited, like from 5 kids, but we kind of expanded the data set using that UX data plus the in the lab test data. And also we try to like expand it, like augment some data based on, again, like what could possibly be happening. You know, we used also some AMT Turker data. So it's a mixture of a lot of things, but it's not real deployment data, not from the in the wide classroom setup. So that's the POC data set. This is the one that we use for training our models. On the right, we have the deployment data set. As I mentioned, we go into the classroom. So we collected like data from 12 kids. It's still not that large, still limited, but this time it's in the wild. So like, I mean, it has a lot more problematic utterances than we expected, of course. So the differences is we have like slightly less number of intents, because some of the intents that we think might happen never happened. Like the kids, we are asking certain questions, the kid will never answer in the, you know, this unexpected track. They don't go into that. So some of the intents are not there in the deployment set. And also the utterances are slightly shorter in real world case. And as you might see, like, I mean, the sample size are more or less, say, around 2K. But like we have less, how to say, we have like, for some intents, we have very few samples, some we have a lot of, so the distribution is quite different. So this shows the class distributions again. So on the left, I'm showing the planting game, on the right, watering game this time, and we try to compare the POC versus real deployment class distributions here. So we have some domain specific intents. I mean, most of our intents are actually very game specific or task specific. Like we are asking the kids like, what would make the meadow look more beautiful? And we are expecting answers like, flowers, daisies, lilies, stuff like that. That's very game specific, and it will happen at certain point only in the planting game. And in the watering game, for instance, we asked like, okay, now we have the flowers, what would make them grow or bloom? So we are expecting like the water as an answer, or variations of it, not just water, but like, so this is again, very, very task specific intents. But among those, we also have some generic, like affirm, deny, like this happen like almost in all dialogue systems, like yes, no kind of answers. And also the out of scope is a big class here, because as I mentioned, since this is a multi-party conversations, the kids or the facilitator, the adult in the room, they're not always talking to the agent, they talk to each other. So when we had the data, when we tag those utterances, we need to tag them as out of scope so that the agent should not answer. So it's like not referring to the agent kind of class. So it's a mixture of almost all other things that we expect. And this is the NLU results. As you can see, the baseline TF, the transformer plus BERT embeddings were performing around 90% for planting and 92% for watering. And when we switch to the diet and using the convert embeddings, we have seen more than 5% improvements this is on the POC data set still. So since this is our training set, we are using tenfold cross-validation here. We don't have a separate test set. And this is a kind of an extensive evaluation on the training set. And as you can see, like switching from transformer to diet adds up around like 3 to 4% improvements, plus switching from BERT to convert adds 1 to 2% improvements. But when we check the deployment data, when we test the same models, I mean, the training, the models are still trained on the POC data, but this time test solely on the deployment data. As you can see, we see a performance degradation around 7% for both games. So, I mean, we are still like operating close to 90, I would say, but it's not like as we hoped for. And the interesting result here is that we still see an improvement with switching from the TF bird to diet convert for planting. The improvement is still 4%, but for the watering game, actually the improvement is like almost, it's not even significant, you know, half point. And as you can see, the standard deviation is also high. So, I mean, when looking at this picture, okay, we still believe that we should switch from, in our STS pipeline, we should switch to the diet plus convert for sure, because it works much better on planting POC, watering POC, and planting deployment. But it's very comparable for watering deployment case. So we don't lose much, but we don't gain much as well. So, and these are some of the errors that we see in the deployment. So, and we check, you know, what is going on here. And we saw that like most of the performance degradations happen for very game specific intents. Like as I mentioned, you know, we are expecting them to say flowers, water, or they can say like anything that belongs to the meadow. Like we are asking what would make the meadow look beautiful or colorful, and they can say butterflies or whatever, like different plants, different animals. These are all valid answers. These are valid in the context of planting game, but these are invalid in the context of watering game. So it's very complicated for the model to really figure out. And also I mean, anything could happen in the real world deployment. So that's why we have seen great degradation in those game specific intent performances. And we also show like the facilitator is actually like explaining the game. But since those utterances in the wild are so like diverse and so different than what we might expect, it can be easily mixed with other intents. Like for instance, here, like the facilitator is actually trying to help the kids to come up with the number. But we also have a very similar intent that the kids are asking to the Oscar, or the facilitator asking to the Oscar, give us the next number. So these are very, very like very subtle differences, and they are semantically very close. So that's why we believe this 7% drop is quite expected. So to sum up, so the aim is building this task-specific STS for younger kids learning basic math concepts. And we still believe the gamified learning and game-based learning is much fun than the usual like traditional formal instructional learning. But definitely if we're gonna like use like right now we have wizard in the loop. So if something goes on, the wizard can intervene. So it's not fully autonomous. We're not there yet. Because it's not just the STS. I mean, we have the vision modules, other modules that can make a lot of prediction errors. So it's not ready to be fully deployed yet. But I think like the results are promising, and we believe that, you know, for the future work, we are right now working on some human in the loop learning approaches. So this is like we are working on like how can we make the clusters more cleaner, like how can we really separate those intents in a better way and do some visual bulk labeling kind of approaches using the human in the loop approach. And also, since we have very limited data, can we use really data augmentation, using some paraphrase generation? That's also another track that we're after. So that's all. And these are some selected references. Thank you.